Welcome everyone. It's nice to meet you all. Thank you for joining today's the Tor Vergata Astrophysics Seminar series. My name is Dawn Kim, and I am the first year PhD student at the University of the Tor Vergata in Apuios. And it is an honor to introduce today's speaker, Professor Goddi. And today, he will talk about the recent amazing results from the Event Horizon Telescope Collaboration as a total of the studying nearby supermassive black hole at the event horizon scale. And he will introduce a new result of the Sagittarius A star supermassive black holes and dwell in our Milky Way galaxies, and also sum up the discussion on the M87's new result together. And as a brief introduction of our speaker, he completed his PhD degree at the University of the Cagliari and studying the kinematic of the water major in star-forming region. Then he started his career at the Cagliari Observatory and Harvard Smithsonian Center for Astrophysics with the Smithsonian Astrophysical Observatories in the fellowship. Then coming back to Europe, he worked in Germany and Netherlands at many institutions, including the European Southern Observatory and JAI. In addition, currently he is on a tenure track at the University of the Cagliari and working together at INAF and INFN. He is currently involved in this and leading the many projects, including the Event Horizon Telescope for studying the supermassive black hole, AGN, and star formation. The main expert field is on the VLBI observations with ALMA and other radio telescopes. Please welcoming again our speaker, Professor Goddi, and now is it time for you, Professor.
Thank you for your patience. So the story I want to tell you today is mainly the story of these two images. The one to the left is the first historic image of a black hole, the one at the center of the distant galaxy M87 the Virgo cluster. We published this image 3 years ago, you might remember. And the second one to the right is much more recent. We published this about a month ago and portrays the black hole at the center of our own Milky Way. And it was actually the prospect of taking this image that motivated this project more than 20 years ago, when the theoretical prediction was made about being able one day to take an image of the black hole shadow at the galactic center. But the story is much more than a story of two astronomical images. It is the story of a technological challenge to build a telescope with the size of the Earth that could work at high radio frequencies to see what was considered invisible. But it's also the story of a group of highly motivated scientists, or very crazy ones, depending on the point of view. Scientists that at different stages of their careers decided to invest everything in a project that was certainly ambitious, but also with a very uncertain outcome. And this is the outline of my talk. I realize I don't have my camera on, so now you should also see me in case. Perhaps it's a bit optimistic for 45 minutes, but I'll try to cover as much ground as possible, starting from the fundamental concepts that motivated these black hole studies. I will describe the instrument, the Event Horizon Telescope, or the EHT. Then I will review the crucial steps needed to obtain these historical images, and then I will briefly summarize the implications of these results and what we learned from them. And if there is any time left, I will talk a bit about the future of the EHT. We all know that black holes exist, and they are one of the most fundamental and extreme predictions of Einstein's theory of general relativity. But since their first formulation by Carl Schwarzschild in 1916, they were not really accepted by the physics community at the time as real astrophysical objects. In fact, a lot of time passed, and they required a number of experimental confirmations, especially starting from the 60s and the 70s. For example, the discovery of quasars, which are very bright objects that appear to us similar to stars, from which they get the name quasi-stellar, but being located at the center of galaxies that are very far away from us, people soon realized that they were not certainly stars. And then the discovery of very powerful relativistic jets that propagate near the speed of light for thousands, sometimes millions of parsecs, therefore going well beyond the galactic centers which they come from. And only spinning black hole, accreting matter very fast, very rapidly, can explain the enormous energy output required to launch them. And then the discovery of X-ray binaries, where a black hole devours matter from the companion. But perhaps the most compelling evidence of the existence of black holes in the universe was provided by the discovery of gravitational waves, published in 2016 by the LIGO Virgo collaboration. These are ripples in the fabric of space-time produced by the merger of two stellar mass black holes. So we had decades of black hole studies that led to the discovery of gravitational waves, which have provided wonderful confirmation of the predictions of general relativity. But even after these historical discoveries, we still lacked a direct proof of the existence of an event horizon, which is the defining feature of a black hole. So in other words, we still had to see a black hole, at least its surroundings. And this has always been and precisely the mission and the challenge of the Event Horizon Telescope. So this is the question where we started off. What would a black hole look like if we could observe it? To answer this question, one needs to take into account the light bending in the warp space-time around the black hole. So this to the right is a black hole visualization from NASA, where the thin bright lines show path of light rays emitted by the material orbiting the black hole. This matter is concentrated in a thin disk, in a thin accretion disk. This is showing in this bright red colors. But you don't see a thin disk here in this image. You see a very warped image of it. And this is due to the black hole's extreme gravity that alters the path of light coming from different parts of the disk. And to better understand why the NASA simulated image has this peculiar shape, I would like to use this graphic. Here on the left, you have a black hole surrounded by a thin disk of matter, and to the right, we have the observer. Now, the portion of the disk closer to the observer forms a thin stretch of emission, as expected for a thin disk seen almost edge on. But it is interesting to notice that the top of the disk behind the black hole is also visible. And this is regardless of the viewing angle of the observer, because the gravitational field of the black hole bends the light rays close to the black hole, and this allows us to see what is behind the black hole. And it's precisely the back of the disk that forms this bright image on the top with this circular shape. Not only that, but the same effect allows us to see the underside of the disk down here, which forms this bright ring of light outlining the black hole at the bottom. And I must point out that the idea of reproducing the appearance of this glowing gas surrounding a black hole is not new. It was introduced in 1973 by Bardeen, and the first computer simulations were done in 1979 by Jean-Pierre Luminet, who was the first one to use Einstein's equations to trace the path of light rays in warp space-time around the black hole. So back to the note, that's too fast. Back to the NASA image. Now you should understand better what we see here. So the top is the back of the disk behind the black hole, back relative to us. And the bottom is the part underneath the disk. And the part that you see in front is the portion of the disk closer to us in a John. And these concentric circles form the photon ring, which is formed by light orbiting around the black hole several times before escaping the black hole and reaching us. And inside the ring is where the light rays are trapped, and that's why we see the dark area. And this is what we call the shadow of the black hole, and this indicates the presence of an event horizon. And for Hollywood lovers, you might remember the image of a Gargantua in Interstellar, simulated by Kip Thorne. This one has a very similar appearance with that of NASA that I showed you before. The reality is, however, a bit different. The NASA and gargantuan simulations assume that the black hole is surrounded by a super hot thin disk that emits very efficiently, and the black hole has a very high accretion rate. In fact, more realistic simulations that reproduce more closely the conditions observed in M87 star and Sgr star, like this movie I'm showing here, show a more thicker accretion flow, so something closer to an asymmetric toroid than a thin disk. And the black hole is a rather starving one. But most importantly, the accretion flow doesn't emit very efficiently. So these are the so-called RIAF models with very low accretion rates. So RIAF is the acronym for relatively inefficient accretion flow models. And this one results in a more puffy accretion flow. And that explains also why we see donuts. This is going faster than I want. The reason why we see donuts and not the beautiful NASA pictures. All right, so simulations are very nice, but the question is, how can we see the photon ring and the shadow, the black hole shadow, with telescopes? And the first thing to assess or question to address in this respect is the size, which is the size expected for the black hole. And from the Schwarzschild solution, we know that the event horizon is proportional to the black hole mass, the size of the event horizon, which in linear sizes corresponds to 3 kilometers for one solar masses. But since we are interested in the angular size on the sky, we need to consider the distance. As you can see here, for one solar mass at 1 kiloparsec, you get something like 0.04 nano arcsecond. These angles are really, really tiny as expected. And this applies both to stellar mass black holes and supermassive black holes, because it's true that supermassive black holes can be millions to billions times more massive, but they're also millions to billion times more distant. So both are generally too small. And it turned out that Sgr star and M87 stars are the only exceptions. Although M87 is 2,000 times more distant, it is 1,500 times more massive. So their event horizons subtend similar angles. So we have about 20 microarcsecond for Sgr star and 16 microarcseconds for M87. So they're still really tiny angles. Likely, the shadow size is a factor 2.5 larger due to the gravitational lensing of the event horizon. So what we get is that the biggest black holes as seen from Earth have angular sizes of 40 microarcseconds and 50 microarcseconds, respectively. So this requires 20 microarcsecond resolution for being observed. And the analogy that I always like to make is that this is the resolution natures of a donut on the moon as seen from Earth. I like to use just because the M87 image looks very much like a donut. Obviously, there is no optical telescope technology that can attain this resolution of 20 microarcseconds. So we had to develop a dedicated and transformational instrument to do this. And this brings me to the second part of the talk on the instrument. I'd like to start from the classic diffraction limit formula, which gives the angular resolution of a telescope with a diameter d observing at a wavelength lambda. And the first question is, what wavelength should we observe? This plot shows a spectral energy distribution for Sgr star. I don't want to enter into the details of the various emission mechanisms that contribute to the spectrum at different frequencies. I just want to point out that the peak falls between radio waves at 1 millimeter and the mid-far infrared here, and this is known as the sub-millimeter bump, and is where the synchrotron emission peaks. The problem is that at these frequencies, which are above 1 terahertz, the Earth atmosphere becomes very opaque. So the best we can do for now is to observe around 1 millimeter, where you see this red light here in the SED and in the Earth atmosphere absorption plot. Okay, so if we consider a wavelength of 1 millimeter and we require an angular resolution of 20 microarc second, we get a diameter of 10,000 kilometers. So we need a radio dish with okay, too fast. My computer today is not collaborating. So we basically need a telescope the size of Earth. Such a telescope is obviously impossible technically and geographically to build. Instead, we use a global network of radio telescopes scattered across different continents, which observe the same source at exactly the same time. They're simulating a telescope the size of Earth. And this network uses a technique called VLBI, which is the acronym for Very Long Baseline Interferometry. And the technique works like this. So our source emits radio waves. This will arrive to a pair of radio telescopes located in different parts of the globe without real-time connection between them. These radio waves will arrive with a very small delay to one of the elements compared to the other. Talking about delays of millions of a second. So these are very tiny delays, and to measure them, we use very precise atomic clocks. These are called hydrogen mazes, and these ones lose only 1 second in 100 million years. And this is required to measure accurately the arrival times of the radio waves in each pair of telescope, because this allows us to synchronize and combine the recorded signals. And we do it a posteriori. So even if the two antennas have no real-time connection, we can still combine and make interfere the signals. So basically, we recreate the interference pattern of radio waves arriving at the two telescopes post factum. Okay. Okay. So each telescope in the network works in pair with another, providing some information about the source. For example, pairs of telescopes that are far apart can detect the sharpest details of the image. And then we can consider different pairs with different orientations, okay, and with different angles. And each different angle picks up different parts of the source. And then if we have enough samples, so we can recover all the sharpest features, okay. And then we can consider telescopes that are closer together, and these are sensitive to broader features than wider pairs. And finally, once all these components of the image are combined, then we can obtain a good representation of the source we are looking at. Now, making a perfect image will require telescopes everywhere, at all orientations and separations, but we only have a handful of telescopes, so this is not possible. And what happens is, luckily, Earth rotates, and the separation and orientation between telescopes change, allowing us to see more parts of the source and therefore to reconstruct an image. And that's why this technique is called Earth rotation aperture synthesis. And the obvious advantage of this technique is that it can achieve the resolving power of a single antenna of the size of the maximum separation between telescopes. Okay. Some of you might know that this technique, VLBI, standard centimeter waves up to 22 gigahertz, but can also be routinely done at 50 gigahertz, even up to 90 gigahertz. However, at higher frequencies, so we're talking about frequencies above 200 gigahertz, corresponding to a 1 millimeter wave, there is a number of important challenges to face. Our first enemy is the atmosphere, in particular the water vapor in the troposphere. The troposphere, the water vapor content, tends to destroy the radio signal at high frequencies. So we need very dry sites at high altitude. Not only that, the other issue is that as I said before, for this technique to work, we need the minimum number of telescopes, but the millimeter telescopes are hard to build because they require extremely high surface accuracies. We're talking about a few microns over sizes of several meters or tens of meters. So they're very expensive and very hard to build. But also they need to be brought to remote sites where the conditions are good enough for observing this high frequency. So we don't have many, okay? And this has been exactly the challenge of the Event Horizon Telescope, to apply the VLBI technique on a global scale, frequencies about 200 gigahertz. And these frequencies were necessary to be able to resolve the innermost regions of a black hole. And this is a summary map that you see here of the globe showing the telescopes that are part of the EHT. These are, they appear virtually connected by lines. Here you can see 8, but the network is constantly expanding. In fact, we currently have 11 radio telescopes. And you will see now some of the antennas that are part of the EHT in this movie, and you will see that these are located in remote sites, which were selected, I was saying before, based on their dry climates. I would like to point out that these telescopes were all existing antennas, so the EHT has not built any of them. That would have required major resources. But nevertheless, we had to equip them with the required instrumentation so they could work in the VLBI network. And this required considerable technological development. So all in all, setting up this network from the first pioneeristic experiments done in 2007, it took more than 10 years of work and cooperation between institutes and countries. And going back to the challenges of millimeter VLBI, we have the problem that the dishes are small. Typically, we have dishes of 10, 15 meters. So they have less collective area when we compare to radio dishes that work at lower frequencies. In Italy, you might know, we have, for example, the Sardinia Radio Telescope, which has a 64-meter diameter. In China, we have an non-steerable dish of 500 meters, which is fast. So radio telescopes working at lower frequencies can be much larger. But we can't build these large millimeter telescopes because, as I said before, we need much higher accuracies in their surface. And this is not only the dish sizes the problem, also the receivers perform more poorly at high frequencies. So all this translates in a quest for higher sensitivities. Okay, and one way to do this, to obtain or to perform more sensitive observations, is to use existing interferometers with lots of dishes to increase the collecting area. This is ALMA, includes 66 antennas located in a plateau of 5,000 meters above the sea level in the Chilean Andes. And being in the Atacama Desert, such a high altitude, it enjoys an exceptional dry climate. And all these factors together make ALMA the most powerful and sensitive radio telescope ever built. And to all of us that started working in the project many years ago, it was clear that in order to capture the images of 87 star and Sgr star, we had to include ALMA in the EHT network. The problem was that ALMA was not built to work as a single dish element in a VLBI array. It worked as a connected element interferometer. So to include ALMA in the VLBI array in the EHT, we joined this project. This was made possible by this ALMA phasing project, or APP, which started in 2013 and developed a beamformer that can aggregate the entire collecting area of the array into a single very large aperture. And this is done by aligning in phase and summing up the signals from individual antennas. Normally, we phase up to 41 antennas. So this is equivalent to a 73-meter diameter single dish telescope. So as I said before, the typical EHT telescopes have a diameter of 12, 15 meters. So you can imagine what we gain with ALMA in terms of collecting area. So ALMA is naturally the crucial element of the array. And if you want to know more about the way ALMA works in VLBI, you can read these two papers published in PSP, the first led by Lee Matthews and Jeff Crew from MIT Haystack Observatory, This first paper focused mostly on the hardware and software of the ALMA phasing system, and the second, led by myself, focusing mostly on the data processing. And we have also a third paper, which is almost ready, and this presents the performance of the instrument at the higher band, higher frequency band, 345 gigahertz, which is the future of the EHT. All right, so once we succeeded to have ALMA and the rest of the telescopes ready, in April 2017, in different teams, we traveled to mountaintops to carry out the observations, reaching all these remote sites, and I went to ALMA, to Chile, to observe with ALMA. And there are many interesting aspects about the way we carry out the observing campaigns with the EHT, but in the interest of time, we'll move on to the third part of the talk, because I'm sure the question you might ask or you might have now is, okay, you have this VLBI network, but how do you get an image from the data collected with the EHT? And there are various steps, and I will try to quickly guide you through the most important ones. First, focusing on data processing, and then on the imaging. Okay. The first thing I'd like to stress is that EHT observations produce large amounts of data to manage. In 2017, we collected something like 4 petabytes of data. So it is a huge amount of data that cannot be transferred via the internet. So we digitize the signals recorded in, so we record these signals and we copy them onto hard drives of 10 terabytes each. And then we literally transport large boxes full of disks and load them in containers and aircrafts. And with just 5 nights of observation in 2017, we filled half a ton of hard drives. Some of them are shown in this picture to the right. So the EHT is really big data science. Right, so we ship these disks to a center, which we call a correlation center. We have actually 2. One is at HTAC MIT in Boston that I mentioned before, and the other one is the Max Planck Institute in Bonn. And here the data from all the antennas are combined in pairs by supercomputer after synchronizing the signals. So as I was telling you before, we recreate post facto the interference pattern of radio waves which are arriving to each pair of radio telescopes. Then once the data is correlated, it is delivered to the calibration teams where we correct the distortions introduced in the astronomical signals by instrumental and atmospheric effects. And finally, once the data is ready, it is handled by the imaging teams, where we reconstruct the source image with specialized software. Okay, before moving on to imaging, let me point out that unfortunately, millimeter VLBI is very challenging, not only in terms of observations, but also in terms of data calibration. And there is again the effect of the troposphere, which reduces the coherence time to just a few seconds. So you can't easily average the data to build up signal to noise ratio. And the other main issue is that DHT is very heterogeneous. So you have stations which have very different sizes and therefore different sensitivities. They have different amounts. They have different slew times. They have other mechanical properties that are very different. Also, the sizes are very different. So this makes calibration of the array very challenging. So we had to develop novel data processing pipelines and algorithms. And this is a part that took me a lot of time during the years from 2017 till 2020 and even now. But I will not discuss this part because it's fairly technical stuff. I would like to speak a little bit about the imaging process. This plot here shows the so-called UV coverage. To understand what the UV coverage is of the UV plane, imagine that this plane is the dish of our virtual telescope. And this plot shows you where you have measurements. Okay, in correspondence of these colored dots. Or if you prefer another analogy, you can imagine this is a camera and the colored dots are showing you the only active pixels, okay, of that camera. So you can appreciate that the UV coverage that we can get with just a few telescopes is very sparse. So the issue is that in order to reconstruct an image, we need to interpolate between measurements, okay, in order to fill the missing information. And in order to reduce bias in this process, we adopted a multi-stage procedure. First, we have developed 4 different imaging algorithms, okay? And these imaging algorithms use different methods and assumptions to fill this missing information. So we developed them in a completely independent way, okay? Not only that, we created different methods, we also used them in 4 different teams, each blind to others' work, and the stage allowed us to avoid shared human bias, okay, to assess common features that will come up in independent reconstructions. And I was part of team 2 in this stage of the work. And finally, we constructed a large suite of synthetic data to exercise the imaging algorithms used by the different teams. And in particular, we consider 7 geometrical models, 3 ring models and 4 non-ring models. And all these models had properties similar to the observed data, okay? And the way it works is the following. So first we create synthetic VLBI data that correspond to these models. Okay? Then we use our imaging pipelines to create images from this fake data. And then we compare the results we get, the images that we get, with the corresponding ground truth images, which are these ones, okay? And through the survey, we could assess the dependence of our images on imaging assumptions from the assumptions made in each of our pipelines or algorithms. And not only that, it allowed us to select a set of optimized parameters to use when reconstructing images of METI7 star and Sgr star. Okay, so we use these fiducial parameters in each of the imaging algorithms. And for METI7, actually, we had 3. The 4th algorithm was added for Sgr star. And as you can see, these 3 images look pretty similar. Since we didn't want to be biased anyways against any specific method, the fiducial image that we published 3 years ago was obtained from the average of the 3 images from the 3 algorithms. Okay. Now, while for METI7 we obtain a single image, for Sgr star the same process resulting in thousands of images, which appear different in the brightness distribution in the ring. And since we could not choose just one image a priori because all images are compatible with the data, what we did was to took an average of these thousands of images, and this is the image that you have all seen. You might ask, why do we get so many different images for Sgr star and not for METI7? Well, this is a consequence of 2 main complications of observing Sgr star with respect to METI7 star. And the first is fast variability with emission. Sgr star is 1,500 times less massive and is therefore 1,500 times smaller than METI7, which means these photons orbit around the black hole 1,500 times faster. Okay, how fast? We can estimate this from the dynamical time scale at the location of the ISCO. The ISCO is the innermost stable circular orbit. And for a non-spinning black hole is given by this formula. So as you see, it's directly proportional to the mass. And if you consider a spinning black hole, it can be up to a factor of 10 smaller if you have the maximum spinning black hole. So while for METI7, this corresponds to weeks, maybe even months, couple of months, for Sgr star is only 30 minutes or even less, maybe a few minutes, tens of minutes. So you can realize that while we observe it, the source changes continuously. Keep in mind that the final image is obtained with the data collected during 1 night of observation. So this is a time interval where the source has changed potentially up to 100 times. Okay, So this partly explains why Sgr star appears less symmetrical and circular and in general fuzzier than EHT. Okay. So to account for this variability, we had to develop new algorithms and perform more extensive testing, which partly explains why it took us 3 years longer to publish the final image. Okay. And of course, we needed methods to measure this variability, and for this purpose, we used ALMA. This ALMA image showcases the galactic center mini-spiral, which are clouds of ionized gas extending for a few parsecs. And the bright source at the center is Sgr star, and below is a light curve on the millimeter emission from Sgr star as a function of time during the course of the same night. These are hours, okay, in this axis. So its flux density varies up to 20% across one single night. But this is not all. The other challenge we needed to overcome is the scattering, because we are looking at Sgr star not only through our own atmosphere, but also through clouds of ionized gas in the disk of our own galaxy towards the center, the galactic center. And interstellar scattering has two components. There is a diffractive scattering, which leads to angular broadening, so your source appears bigger than its intrinsic size. Refractive scattering leads to spurious substructure, as you might appreciate in the simulated image. And this component is refractive scattering component is more insidious because it is stochastic and it's time variable. Okay, and this partly explains why the image we got for Sgr star is fuzzier and blurrier. Scattering is responsible for hiding crucial details, such as a sharp ring, as I would expect theoretically. And this picture illustrates best the differences in imaging Sgr star in comparison with EHT. The scattering effects can be thought as an image behind the window on a rainy day, and the fast dynamics is represented by a dog chasing its tail. Okay. EHT is instead our nice setter that remains still inside the house, very easy to take a picture of. Okay. A last point on the image of Sgr star that I like to make is that we realized that we could cluster the recovered images into 4 categories based on similar visual features. 3 of the clusters contain a ring-like feature showing a peak at different position angle around the ring. Okay, but there was also a much smaller 4th cluster that contained images that did not appear to have a ring. Okay, this amounts to only a few % of all cases. And then what we did was to take first an average of all the images in each cluster, the 4 that you see down here. Okay, and then we took an average of these 4 images weighted by the percentage of their appearance, and this is the image that you see on the top. And this is exactly the reason why the final image shows these 3 brightness peaks in different position angle of the ring, because it's an average of the first 3 cluster images which have a peak in different position angles, right? So once you make an image, an average of these 3, then you get this this structure. This one is also part of the average, but again, since it's a few %, and the average is a weighted average, it counts less in the average image. Okay, so we can't fully rule out these few % cases without a ring, but we can for sure say that the vast majority of the images contain a ring of exactly the same size, which is 50 millionths of an arc second, which is the angular size predicted by GR for a black hole of 4 solar masses at 8 kiloparsec from us. Okay, and to reach this conclusion took us years of testing, counter-testing, and discussions of all kinds to be sure that what we were seeing was indeed the shadow of the black hole at the center of our own galaxy. Okay. Okay, I realize I have already spoken about 35 minutes, so it's quite long on these 3 parts. You must have realized by now that the EHT is a project based on data acquisition and data processing, so I really want you to take that point home from this talk. Suppose many of you were maybe more interested on the scientific interpretation and implication of these EHT images. So I can try to cover these aspects in the next 10 minutes or so. I'll try to go fast to make up for the time we lost. What we can say now is that black holes are not just abstract concepts or solution to an equation, but they are a laboratory that we can use to study accretion process in black holes or the formation of relativistic jets. Most importantly, we can observe them with telescopes to understand gravity. And we have a very active theory working group, which built a large suite of theoretical models from which we created a library of over 60,000 different simulated images for MHD7. These are created using GR MHD models, so these are general relativistic magnetohydrodynamic models, to assess physical conditions of the plasma accreting onto the black hole. And then we use radiative transfer models, that is ray tracing codes, to model the corresponding electromagnetic emission. And this way we create all these nice images. And each image uses different parameters, like slightly different masses, different black hole orientations, different magnetic field configurations, different plasma temperatures, different electron temperatures, and so forth. And this is why they appear all different. Some have more structure, some have different dosimetry than others, but they all have one feature in common: a bright ring with a dark spot in the middle. And that's the GR signature of the black hole shadow. So what we do then is to compare these models with the observations to determine the source parameters with the highest confidence that we can. For Sgr A, we have produced even a larger library. This was necessary for the complications I mentioned before, like the time variability. So we produce about 2 million simulated images at 3 frequencies: 30 gigahertz, the ones that you see here, at least a part of them, at 86 gigahertz, so a lower frequency, and at 2.2 micron. Okay, and then we compare these images with 11 different observational constraints. 6 are coming from the EHT observations, and the others are coming from other instruments like the GMVA that works at 86 gigahertz, and Keck, and the VLT, for example, images at 2.2 micron. And excuse me. And what we found was that the best bet models are strongly magnetized. These are MAD models. They have a positive spin, so they are prograde black holes in the sense of rotation. They have low inclination, and they have accretion rates between 10 to the minus 8 to 10 to the minus 9 solar masses per year. Okay. Excuse me. Okay, besides these black hole accretion models, perhaps the most relevant question here is whether what we see is consistent with GR or not. Qualitatively, we can already say that what we see, this bright ring around the dark patch at the center, is consistent with emission from the photon ring around the black hole and the shadow, okay, as I introduced before. But we can be more quantitative and extract parameters from our measurements and see how they compare with theoretical predictions. In particular, we have used 3 independent methods. We fit the geometry models in the visibility planes, so directed to amplitudes and phases that we measure in VLBI from the combination of waves arriving at the single telescopes. We measure the brightness distribution in the image. We use GR MHD simulations. I will quickly mention only the middle one because it's more intuitive. From the image, we can measure the size, the shape, and the symmetry in the brightness distribution, at least for MHD7. For Sgr, I told you that these 3 peaks are a spurious effect of the imaging process, while for MHD7, the brightest portions of the ring can be explained with the GR effect, which is called Doppler beaming or Doppler boosting. Plasma moving towards us boosts the emission in our direction, and plasma moving away from us produces dimmer emission, so in this part of the image. So in this case of M87, the asymmetry is telling us that the gas is moving clockwise, okay? And we can then compute the size and the shape of the black hole shadow fits in the peak of the brightness distribution in the ring. In GR, the size of the black hole shadow depends on the mass, while its shape, which is approximately circular, within a few percent, depends on the spin. Since we cannot measure circularity to an accuracy better than 10%, we cannot determine the spin from these images, not yet at least. So we focus only on the mass measurements, but we can come back to the point of the spin if you have questions later on. Okay, and using the same equation that I introduced in the first part of the talk for the Schwarzschild angular size and assuming a distance of 16.8 megaparsec, this is coming from previous measurements, we obtain a mass of 6.5 billion solar masses. Okay, and now we can compare this estimate with previous measurements, and there are actually two measurements of the mass of the nucleus of M87. One comes from gas dynamics, observing the alpha line with the HST, Hubble Space Telescope, in a disk within a 40 parsec from the nucleus. And the other one comes from stellar velocity dispersions. So these are stars that are orbiting the black hole at a typical distance of tens of light years. Okay, so something within 60 light years, which corresponds to 20 parsec. Okay, so both these estimates use Newton's law of gravity. Okay, so you see there is a factor of 2 discrepancy between the two. So clearly the size of M87 in our image is in strong agreement with the estimate from the stellar velocity dispersion. Okay, and this is great. It's a great result, and to understand, let's see if I can move on. And for you to understand the beauty of this consistency, think that here to the left, we are showing a region that is 40 light hours, okay, across. This is the time that a photon takes to pass across the event horizon, which is assuming a specific value of the spin. So our estimate is based on the gravitational field exerted on photons very close to the event horizon. But then if you look at the stars, these are orbiting the disk about 60 light years away. So they are probing far field region. And assuming the mass from stellar velocity dispersion is correct, this is a key test of GR, because the theory of gravity is valid both at large distance here in the weak field regime and also near the black hole horizon, so in the very strong field regime. For Sgr star, we can do a much more stringent test of GR, because we had a much more precise prior of the mass and the distance, thanks to this study that has followed the orbits of about 30 stars in the galactic center, which appears to be moving very, very fast, thousands of kilometers per second around the dark point. And just using Kepler laws to different groups using the VLT and the Keck telescopes in the near infrared, we're able to estimate the mass of the dark object in about 4 million solar masses. And these are the last published values of the mass and the distance of Sgr star from the Keck and VLTI groups. And as you can see, there is actually a difference of about 7% in the mass, which is larger than it used to be. Anyways, we can use both these priors, so these m over g values, to get an angular size of the gravitational radius, which is about 5 micro arc seconds using the two priors. Remember that Schwarzschild radius is two times the gravitational radius, and that the shadow has a radius of about 2.5 times the Schwarzschild radius. So the shadow diameter is 10 times this value. Okay, so it's about 50 micro arc seconds. And so for Sgr star, we could quantify deviations from the Kerr metric using these two priors. These plots show the posteriors on the parameter that measures the deviation from of the black hole shadow size that we obtain for Sgr star from the Kerr prediction. And the top panel uses the prior from Keck and the bottom from VLT or VLTI. and the various curves correspond to different sets of theoretical models and different imaging methods. And this purple shaded area shows a range of about 8% predicted for the Kerr metric. This depends on the black hole spin and the observer inclination. This is because black holes with a non-zero spin at different inclinations can have a shadow sizes that are smaller by up to 8% from the Schwarzschild limit, which is the non-spinning black hole. And that's the zero. The zero that you see in this plot is Schwarzschild. Okay. Anyways, the conclusion of this analysis is that the observed image size is within 10% of the Kerr prediction. Okay. So the conclusion of this analysis is that the EHT images are in excellent agreement with general relativity. In particular, the size we measure in both black holes are consistent with the Kerr metric within 10% once we adopt independent measurements of the mass and the distance of these objects. And this particular statement is quite amazing because the two black holes could not be more different. Okay, Sgr A, as I said, is 1,500 times smaller and less massive than M87. In fact, here you can see that while M87 encloses the solar system region larger than our solar system, Sgr A encloses at most the orbit of Mercury. M87 is accreting mass at a rate that's 1,000,000 times larger. It drives a powerful relativistic jet, while Sgr A does not. And they reside in very different galaxies. M87 is an elliptical galaxy. The Milky Way is a spiral galaxy. They have very different ages. So based on all these differences, it would have been plausible to see differences, okay? But we don't. The region near the edge of these black holes looks very similar in both objects. And this suggests us, indicates us that the source properties around the event horizon are determined by the space-time metric. Okay, in this case, it's a Kerr metric. Okay, and not from the physical properties of the material around the black hole. So I'm well past 45 minutes, and I think this is a good note to end my talk. So thank you all for your attention. I hope you enjoyed the talk.